All right, we're live. I've wanted to do this for a really, really long time, and it is an absolute pleasure to welcome one of the most fascinating people I've had the pleasure of working with. Today, not in the studio, we're in the lab. Today, I've got Mr. Winfried Hensinger. How are you doing? It's been years.
Good. Nice to see you. Excellent.
Yeah, it's only been about 1 billion years since I've been here. Isn't it?
Indeed.
To give people a little bit of context who are listening at home, a question I'm often asked doing music is, if I wasn't doing music, what would I do? What would I choose as a profession? And I always say without a shadow of a doubt that I'd probably be in a lab somewhere in Sussex helping build quantum computers with a guy called Winnie. And I think it's something in my life that I've been really passionate about, and it's nice to have a platform to actually start discussing it a little bit more. And especially seeing what you've been doing now with your work on your lab. I mean, you've been around the world, you're going to BBC, you're doing Radio 4, you're on Sky News the other day. I mean, how have you been? How's life been in the world of quantum mechanics?
Yeah, so we're trying to build a fairly elusive machine. It's called
It seems so, yeah.
quantum computer, which relies on a very, very strange theory called quantum physics. So quantum physics has been referred to as spooky by Einstein because of some of the very strange predictions it delivers. Yeah,
I mean, diving straight into that, that's something that's affected me for all these years. I mean, it's been a long time since I was here at the University of Sussex. But one of the things that bothered me more than anything, and it genuinely still bothers me today, is this concept you taught me about of quantum entanglement. And the best way I can do of explaining it from what I remember is this idea that if you imagine subatomic particles have got different properties, for example, we call one spin, like an electron can sort of spin up or spin down, depending on whether it's orientated with a magnetic field or otherwise. You taught me that if one of these things is spin up, you can entangle it with another one that might be spin down, right? And the idea is that these guys and girls, you can separate them across any distance, across the universe if you want to. And if you knock one of them, the other one instantaneously goes the opposite direction, which is basically magic, isn't it?
So it's an instantaneous connection, we say. So if two particles are entangled, and if you, say, measure the state of one of them, you'll immediately do something to the other particle. So it's very strange, and that's kind of one of the reasons why Einstein was thinking there's could be something wrong, and came up with plenty of experiments trying to disprove quantum physics.
I mean, look, it's been years since I've come here. I was really hoping you were just gonna be like, yeah, we know how that works now. So you don't know how that works yet, like, because obviously you're doing the calculations, you're starting to build computers, you're using this concept in a really intricate way. But this particular magic thing that's happening between these particles, we still legitimately don't know how this is working.
We do know how it works. We do know the equations. What is hard is to get a physical intuition. So it's very difficult. Some of the phenomena of quantum physics, like in quantum physics, we start with something easier than entanglement, that is superposition, which is that an object can be two different places at the same time. So you can be sitting here having a chat with me and having breakfast at home at the same time. That is perfectly acceptable and possible according to quantum physics. We don't see that with big objects like yourself, but we do see that on a small scale, on individual atoms.
This is the moment where people at home listening, they're probably going to be like, hold on, rewind. Like, so you're saying that things can be in two different places at the same time. Like, is there a way that you can kind of boil that down? And how does that work?
It's quantum physics, which really describes reality, is very counterintuitive. And what is intuitive is what we observe in our environment. So quantum physics doesn't happen in our environment because there's an effect which destroys quantum effects. And that is the air around us, air molecules around us, they hit our bodies or object around us, and they stop these quantum effects from ever taking shape.
Yeah.
However, if you isolate a quantum system, say, for example, an individual atom, if you isolate it well enough, then it can suddenly behave very strangely. And it literally can be at two different places at the same time. So we can do experiments where the only explanation of what we see is that one atom has been at two different places at the same time. So that's very, very strange things, but we can do experiments where we can see that. And in fact, the theory of really of everything, which is what quantum physics in a way very much represents, builds on these very strange phenomena in order to then allow us to understand things we see in daily life, like the colors of objects, conduction in say a conductor, properties of materials like thermal properties, but even the way you can see or smell is because of some quantum phenomena, and you can only understand really how you can see and smell if you include these very strange phenomena.
So if my memory serves me well, and I don't have the best confidence in it, but I'm going to try my best. A lot of people maybe remember from school this idea of having an atom, and you might have an electron that kind of orbits it, and we are used to thinking of these things like they're things, like objects. Like an electron's a little thing, and it goes around the orbit. Now, they had an experiment, which is a famous experiment called the double slit experiment, and the idea being we were trying to decide whether these tiny particles act like particles, like I've just said, or waves. And the idea being that if you sort of shot an electron through two slits that were really, really close together, the electron would pass through one or the other. That was the assumption because we treat them like particles. And what we actually saw was on a screen on the other side, we saw like an interference pattern, which basically told us that the singular electron was actually taking both paths, traveling through both slits. The waves of them were interfering with each other and creating an interference pattern. That's
exactly right. As soon as you either try to attempt to see which path the electron is taking...
That's crazy, isn't it, though? Like, that bothers me so much.
Yeah, quantum physics is strange, very strange. People have spent 50 years trying to get their head around it. And only maybe in the last 20 years... some physicists like myself have actually started trying to tame these very strange effects to build technology with it. And one of these technologies is a quantum computer. That's what we develop here at Sussex.
Okay, so boiling it down, and taking it back to the simplistic, if we are imagining now that we have an electron that can literally be in two places at the same time, it's the same electron, but it has this probability distribution of existing in different positions. When it comes to this idea of quantum entanglement, which seems to be one of the key things that's used when you're processing with computers, the idea, am I right in saying that that in an entangled system, like we said, if you imagine the spin-ups and spin-downs, they can only exist in a particular orientation? Is that kind of the gist of it?
So spin... maybe it's a bit better to think of it a bit easier. So just think of a property, like and of any kind of property of an atom. And spin is basically just a physicist's word to describe, say, the shape of the trajectory of the electron. So let's just think of trajectories. So if I entangle two ions, or two atoms, an ion is a charged atom. So if I entangle these two, then by me knowing something or getting some information on the trajectory of the electron in one atom, something will happen to the trajectory of the electron from the other atom.
Through pure magic. It just happens.
Magic is one word for it. But yeah, absolutely. It's what makes it magic is that you can fundamentally show that the trajectory is not one or the other, in either of these two atoms before we look at one of these two atoms. But when we look at one of these two atoms, we also force the trajectory of the other atoms to become a certain value. So that's the kind of strange thing. So say if I have two entangled atoms, they may be both in a superposition of both electron trajectories or both spins, right? So if they're entangled, they would be both in the superposition.
Yeah, okay.
And when you look at each atom individually, you'll always see that they are exactly in such a superposition state. If you, however, now make a measurement on one of these atoms, and say, for example, it's one spin on one trajectory, then the other atom, wherever it is, on the other end of the universe, will now suddenly also be in that same trajectory or spin state. And that's the very strange thing.
So this is almost like saying if I had a coin and I flicked it and it was kind of spinning in the air, it's a weird superposition of both heads and tails.
Exactly.
You're watching it spin, you don't know which one it either is, but you know it's 50-50. And if this coin were entangled with another coin doing the same thing, they're both in this superposition, heads or tails. Now, if you stop one and look at it, it decides really, doesn't it? It goes, oh, I'm going to be heads now, or I'm going to be tails now. And you instantaneously know the value of the other coin.
So actually using coins is a very good way to think of this. So
I had a good teacher. Sorry.
Absolutely. So if you have two coins, imagine if you have two coins, and so you throw each coin, it always becomes a random outcome, right? So if I have a coin, throw my coin, I get sometimes heads, sometimes tails. You have your coin, you sometimes get sometimes heads, sometimes tails.
Yeah.
Now, if these two coins would be entangled, then the output of your coin tosses would always be random. You could not see any kind of system of whether you get heads or tails.
Yeah.
If I look at my coin tosses, I could not see a system whether I get heads or tails. It would be completely random. But strangely enough, we would always get the same outcome. So you always get heads when I get heads. You get tails when I get tails. And there's nothing, you could look at this coin, you could do any kind of experiment with this coin, it would be a perfectly balanced, fair coin. There would be no manipulation. There would be no information traveling between the two coins, yet they would always deliver the same outcome of a coin toss.
You know what it makes me think of? Because naturally this subject can seem a little bit daunting, can't it? Like even when we're discussing then earlier, it can easily go down the rabbit hole into this confusing world, talking about superposition, stuff like that. But when you actually take it for the face of what it is, and you think about that coin situation for a minute, how are we not all going like completely loop-de-loo about this? It's like, what's the best way of putting it? I mean, imagine if I had my phone and I dropped it and it just flew up to the ceiling, like everyone would just lose their minds, because it's such a crazy concept that it defies every part of logic that we have as humans. Yet this is happening all the time, and you now use it to do stuff. Like I think that in essence is why ever since I left uni and through all my time doing music, I've always been bothered by that. And it's something that I don't think's ever gonna not make my head scratch. You know what I mean? Like I'm so confused by it.
I think when you do a school in physics, you tend to do really boring stuff and you calculate really boring things like a mass on a slope, and you calculate a velocity or something. What you're often not being told is some of the really mad, crazy stuff. And actually, you do learn about this stuff, but you typically learn about this stuff in Star Wars or Star Trek. And
I heard teleportation's a thing now, though, isn't it?
We teleporters, we do that. We do that in the lab.
Yeah, just looking at me like, what? Like, teleportation
is a thing.
The technology, the process of it is understood now. Like,
and we can do it.
If you were to try and describe this to people listening at home who might not have any background in physics or any background in quantum mechanics, could you try and put across, like, how does teleportation work?
So unfortunately, teleportation only works with individual atoms.
So at the moment,
one
only
atom
on
at a
something
time.
very, very small.
We can teleport one atom at a time.
Yeah.
Now, in a way, this is something which, again, is completely mad. Like, you wouldn't really think that is something which can ever happen, but quantum physics actually enables that very thing. So in quantum physics, we can teleport individual atoms. But
when you say teleport, you literally mean it disappears and pop, somewhere else.
Yeah,
teleport.
We have to destroy the quantum state on one place in order to direct the quantum state in another place. So we can't, as in quantum physics, something that's called the no cloning theorem. Right. That predicts us to just double up. Otherwise, we could just teleport, and instead of having one Scotty on the Enterprise and one Scotty on the planet, have two Scotties, one on the Enterprise and one on the planet. So teleportation means you actually have to destroy one Scotty on the Enterprise in order to get Scotty to become part of reality on the planet. And so this is actually very similar to what we do in quantum teleportation.
Am I along the right lines of thinking that if we had the ability to, which I'm assuming we don't now, but if we had the ability to track the position of lots and lots of atoms, is there what's the best way of putting this? Is there like a natural reason why we couldn't teleport bigger and bigger things? Is there a reason why it can only be an atom? Or could you teleport a water molecule or a helium? Or then could you get bigger and bigger and start?
I mean, never say never. But right now, it's hard enough to teleport just one atom at a time.
Because it's
and
unstable,
only particular species. So in the way we have to manipulate atoms, we have to hold them using electric fields. And so this sets a lot of constraints, and that stops us from, say, teleporting large objects. So right now we have to really teleport one atom at a time, and particularly only one atom species as well. So that really
Sorry, what
limits
do you
us.
mean by species?
So you know how there's different
isotopes?
different atoms, like
Right.
you have hydrogen or terbium, which is a heavy metal which we use in our lab, or there's plenty of other elements, and so we use one particular element called ytterbium. It's a heavy metal 171. It's a particular type of element which is very useful or very convenient when we do the experiments using trapped ions, and so that's the element we use. And so right now we can only teleport ytterbium atoms. So unless you be made entirely out of ytterbium, out of one atom at a time, we couldn't teleport you yet. Now one could imagine maybe using some of the same principles to teleport larger objects, but we're extremely far away from that. And so by no means are we using teleportation right now to transport things. We use teleportation as an ingredient within a quantum computer, and also as a testing ground to test some of the ideas of quantum physics.
I suppose in principle, just the fact that technology is understood, I find mind-blowing, absolutely mind-blowing. You know, obviously a while ago when I was here, part of my work was the microfabrication of chips that, like you said, when you're talking about trapping ions. And I remember all that time ago, popping some champagne on trapping one ion. That was kind of the key. It was, could we build and fabricate this tiny little chip that had the capability of like a little spinning mag trap, which is basically like a magnetic field that would hold this thing in place. It's quite some time ago. Where are you now when it comes to, because I suppose where I'm going with this is now we understand a little bit about how spooky and crazy this world is. We start to move into how do we actually apply that to make a computer. Do you know what I mean? So you're now trapping multiple ions, still one ion. Where are you at?
So maybe I should explain a few things first about quantum computing. Or what is a quantum computer before we get onto the technical details. So while for many years quantum physicists try to just get their head around understanding quantum physics and some of their very strange predictions, maybe 20 years ago, people started to float the idea of would it be possible to tame some of these quantum effects in order to build a machine, a computer that could do certain calculations where even the fastest supercomputer in the world may take billions of years to calculate. A quantum computer might calculate this in a few hours or days.
And by tame, you're talking about this superposition of states, this idea of the coin. It's not down or up, it's both. It's
That's right.
kind of non-binary in that sense.
Think of it this way. So a classical computer, conventional computer, encodes information in what we call bits.
Gotcha. Ones and zeros,
exactly
like
right.
the Matrix.
It's a chain of zeros and ones.
Yeah.
And if it is a very long chain, I can encode a lot of information in that. So it's kind of a language, really. It's a way of encoding information, just like letters
And
are,
also,
numbers are.
and also processing, right? So when it comes to calculating, I imagine it like if you've got a string of bits, it represents a number, say. And
Exactly right. So if I have 2 bits, imagine the world's worst memory stick, which just has two bits, right? So I can write in, for example, 01 into my memory stick, the 2-bit memory stick, and it's full. And so now if I take that information from a memory stick in the processor, I can do some kind of calculation with, and out comes my result out of the processor, right?
Okay, yeah, I'm with you.
So imagine I have 2 quantum bits.
So hold on. As soon as you say that, you're now talking about either an electron with the spin property or a nucleus of an atom, you're now talking about something that isn't necessarily a 0 or a 1. It's a blend somehow of both of those.
Okay, so quantum bit can make use of superposition. Rather than just like a classical bit, which is 0 or 1, a quantum bit can be 0 and 1 at the same time.
Like
just
our spinning coins.
Exactly, a spinning coin can be heads and tails simultaneously. In terms of a quantum superposition, an object can be at two different places. Or a bit can be 0 and 1. So all of that is represented by this very strange idea of quantum superposition. That rather than you being sitting here, you can be sitting here and have breakfast at home. An atom can be on the left and on the right. A bit can be 0 and 1 at the same time.
I think a lot of people at this point might be begging the question, well, why is that useful? Because at least with a computer, you've got zeros and ones, you've got answers, you can process stuff. If you're now dealing in a system, and obviously I'm just playing devil's advocate here, but like in a system where it's a superposition of both, what's the use in that? Is that not more confusing?
So let me get back to the memory stick.
Okay.
So a classical memory stick has 2 bits, and I'm gonna choose to write 0, 1, for example, into my classical memory stick. If I have now a quantum memory stick, so with 2 quantum bits, rather than just writing 0, 1 into my quantum memory stick, I can write 0, 0, 0, 1, 1, 0, and 1, 1 all simultaneously into my 2-qubit memory stick. So a classical 2-bit stick, I can just write in one number. So for example, 0, 1.
Yeah.
Or 1, 1, but I have to choose. I can only write 2 bits, and so I, for example, say 0, 1.
But then why is this superposition useful? Because here's what I'm thinking, right? I've got 2 options. I've got to send some data or do something. I've got my classical way 0, 1. Okay, that's all I can write, but hey, it's a thing, and you know the answer is 0, 1. If I'm now going to go and plug in these 2 bits, which are neither 0 nor 1, they're both.
But they are 1 and 0.
Okay, so
they're not neither. They are actually both.
But then,
so take the two quantum bits. So you write in 0, 0, 0, 1, 1, 0, and 1, 1 all at the same time. 2 classical bits, 0, 1. 2 quantum bits, 0, 0, 0, 1, 1, 0, 1, 1. Imagine you have 3 quantum bits. Then imagine all the combinations you can write simultaneously into 3 bits. There's already 9 combinations. 0, 0, 0,
I'm with you. So
0,
it's
1,
like
0, 0, 1, 1, and all these different combinations, all you can write simultaneously into these quantum bits. And now as when you take them, these classical bits, and you take them through the processor, so you do one calculation, say you add a number to 0, 1, and then the outcome is the answer. With the quantum bits, because you can encode all the numbers simultaneously into your quantum bits, you can do all the computations simultaneously as well.
And is the assumption there, because maybe I missed something, but is the assumption there that they're also entangled?
No.
They're not necessarily entangled either?
No.
Because
just think of it this way. Like, just think of it like rather than just doing one computation at a time. So imagine, for example, I want to do lots of different calculations. Imagine I want to always add a number to whatever is my input. So so imagine, for example, I want to add something to 0, 0. Right?
Okay.
So I write into my input memory 0, 0, then take it to the processor, which adds a number, and out comes the result. And I'm done.
Yeah.
But now I want to do the next calculation. So I want to now have 0, 1. I want to add something to 0, 1. So again, I'm going to take this for the processor and get out an answer.
I'm with you now. I see. So
imagine in a quantum computer,
you get them all at the same time.
I get them all at the same time. Because I can encode all the inputs simultaneously into my quantum bits rather than doing it one at a time.
Oh shit, that's cool. Now, okay, and that brings me on to when I was doing a little bit of research around this, before this talk, and one of the things that seems to be a bit of scaremongering, but we can sort of like get it from the real source here, is that once this ability would be harnessed, you can start to do a couple of computations that classical mechanical computers would take years and years and years to do, and there's all of these kind of millions of years, or maybe even billions and trillions of years, and there's a lot of skepticism around security with things like code breaking, things like banking systems, things like what happens when someone has a computer that's so powerful it could kind of crack any code. Is there any legitimate concern and fear of where this technology is going to end up, or is it really not like that?
So when you put your credit card details on the internet, you use a protocol called RSA encryption.
Gotcha.
And the reason why your credit card details are safe is because the encryption makes use of a very complicated mathematical problem that incorporates factoring large numbers.
Yeah,
so factoring,
which is
factoring
exactly the
means,
sort of problem that a quantum computer would be great at, I assume, because that's
exactly
like
the point. So a quantum computer can break all common current encryption protocols, and that's one of the reasons why people were very interested to develop quantum computers. Security services, intelligence agencies are very interested in that, because you could break any kind of encryption, any kind of current encryption anyway, with a quantum computer. Now,
so when some special secret service people turn up here, slipping bags of cash under the table and making sure that's
so unfortunately, to build quantum computers that aren't capable of doing that will take still a long time. But it's not really. Think of quantum computers like computers.
Yeah,
like you have computers nowadays in hospitals, and they're helping save patients' life, right? You have computers also in nuclear warheads steering the warhead to its goal. Computers can be used for many, many different purposes. And quantum computers, in the same way, can help us understand protein folding, and that may help us find a cure for dementia.
Yeah.
Quantum computers may help us with optimization problems where we don't have any answers. Quantum computers can help us to create new pharmaceuticals. But equally, quantum computers can break encryptions.
And what about when it comes to security? If we really want to hyper security, surely this idea of entangled electrons over space and time using this magic, that's got to be a flawless encryption, surely. So
there is yet another technology called quantum cryptography. And that actually makes use of quantum effects in order to provide communication that is truly secure by the laws of physics. So you can make communication that is guaranteed to be secure. But that wouldn't use RSA encryption. That makes use of this new technology called quantum cryptography.
Wow. And going back to what you were talking about with protein folding, what is that?
So protein folding is a process in biology which is extremely difficult to compute. Let me make 2 steps back. And that is, if I want to summarize many challenges of scientists around the world in numerous fields, is to simplify a particular scientific problem in such a way that it becomes possible for a conventional computer to do the theory behind these experiments. The problem is with the theory, because it you need the full quantum mechanical equations in order to fully understand these problems. That becomes very quickly intractable, impossible to calculate for even the fastest supercomputer in the world. So what scientists have to do is they have to come up with approximations in order to solve these problems. Mm-hmm. However, these approximations are sometimes so severe that you can't trust the answer anymore. Yeah. That's the reason why people have laboratories where they have to do experiments. Why wouldn't they just go out and solve some of these problems on a computer?
Because it's that complicated.
Exactly. And quantum computers now offer the possibility to simulate these systems, exactly making use of a full-scale quantum system, making use of the capability of a quantum computer. And so this is really like a step change in the way how we're going to tackle problems. And so this is much broader than just a single problem class. It just means like we can understand chemical reactions, we can maybe create new materials, we can understand what goes on inside.
And this comes from really modeling it, really. It comes from actually being able to have the processing power to actually be able to model, for example, what happens between these molecules. How do these bonds work? Like,
it allows us to model exactly other physical systems like molecules.
So you're modeling, because I'm assuming that covalent bonds and all the stuff we learned about in chemistry, this stuff is all quantum stuff. It operates through those rules of nature. So if you're intrinsically figuring that out from a quantum system, I can sort of see how...
Basically, if you're trying to solve the equations of some of these systems on a conventional computer, you very quickly run out of steam, even with the fastest supercomputer. So in order to solve it anyway, you have to impose severe approximations, which then render the calculations sometimes useless in the first place. So it's kind of, you run against the wall.
It's kind of just starting to sink into now that you're saying that, I'm kind of taking a while to process it, because what you're saying is you can almost imagine a time in the future, maybe not even that far away, when a lot of molecular bonding, or maybe things that are happening in our blood, or the way that drugs react with your liver, and or the way that you're going to start to uncover exactly how that works, instead of just relying on the trial and error of applying a drug to someone and seeing what happens. And do you know, have I got that right? It's like kind of a big
it's
deal.
maybe 3 steps before that. So when when people develop drugs, they go in a laboratory and they put things together, and then they see what's going to come out of that. And what quantum computers allow us to do is to actually preempt some of these experiments.
To model that before
we even do an experiment. Obviously, later on, we're still going to have to trial these in multiple iterations. So don't think of a quantum computer as some kind of wonder machine that can just solve all the problems. But it's far from that. It's the way I like to describe it sometimes is before we had invented a camera, people painted pictures of people, of things, and some of these paintings, if you actually look in history, they're amazing. They're the most beautiful paintings, and you wouldn't sometimes even know that this is not a photograph, right?
Yeah.
But then suddenly somebody invented a camera, and suddenly it became easy. You just went everywhere and you took one picture, and that picture was just always better than even the best painting you'd ever seen of that particular object. And so quantum computers are kind of like a new tool that allow us to understand and trying to tackle problems in science, in general, in nature, in a complete different way, the same way as a camera allows us to look around and to see things in a complete different way than it was possible before using a pencil or using paintings.
And I'm right in thinking that you actually have one. You're actually running them. You're figuring out problems. You've actually constructed a quantum computer. I mean, I think you were on Sky News a couple of years ago. I watched on YouTube where you were basically saying that you would design the blueprints for people to be able to actually construct and operate a quantum computer.
So quantum computers, because of their tremendous opportunities, have been, in a way, viewed as one of the holy grails of science.
I can see why,
for
sure.
These reasons. And so people around the world desperately tried to build quantum computers using different methods.
Yeah.
And a few years ago, we were very successful in inventing a new way to do quantum computing using trapped ions. Previously, people have used laser beams to do computations on a quantum computer with trapped ions. So for every atom, for every ion, which then forms one qubit, you need 2 laser beams. So imagine you have a billion qubit quantum computer, you would need
a football stadium,
billions of laser beams, and you'd all have to align them onto position of each of these billions of ions. Imagine trying to build a machine like that. So what we invented here at Sussex.
That would be a huge.
That would be
football field. We're talking
much bigger than football fields, and nobody could ever build. Could you, Mark? If I ask you to align a billion laser beams, could you make a machine like that?
Tuesday afternoon.
Perfect.
Easy.
All right. No so I'll hire you then. Might stop the music career and come back to the lab. So if you're able to do that, you're much better than any scientist around the world, because I think most scientists would think that is a very, very difficult thing to achieve, or nearly impossible. You can do this with maybe 10 ions,
but not with the amount
billions of ions. You've already seen in the lab how many mirrors and optics are required just for a few laser beams. So doing this with billions of laser beams, I think, would be very challenging. So what we invented a few years ago was a technique where, instead of using laser beams, we use voltages applied to microchips to execute quantum gates.
And this is something that can be scaled to a much smaller size, I'm assuming.
So that to much larger number of qubits. So imagine if you don't have to have 2 laser beams for every ion, and then you need a billion ions, you need a billion laser beams. So you could then very easily scale this up to billions of qubits. Now, based on this idea, we then went together with a team. We led a team of scientists from around the world, and people from Google, from Aarhus University, Siegen University, Riken in Japan, and us. And together, we drew up the very first industrial blueprint of how one could actually build a practical quantum computer.
And sorry to interrupt, but I get a real buzz from this, because it's like this is something that I think is so beautiful and such a big thing to share. It's just the collaborative attitude that comes out of this. It's like you're talking about essentially an international congregation of people who are just going, look, hey, we're into this, yeah, let's combine. And when you create these blueprints, it's essentially open source, isn't it? You're essentially saying, look, hey, have at it. Let's make a community where we're just going to try and figure this stuff out.
So what we did indeed is we published this in an open way and made this accessible for everybody to look at and to dig deep into and so after around leaving this in the public domain for 3 years, we took on a lot of criticism. We worked on these things and eventually
Why
published
criticism?
this.
When you say criticism,
Science always works by scientists critically looking at the ideas of others, and that's a very healthy thing.
Oh, I see. So it's not like, Winnie, you're an idiot for making it wasn't criticism.
It's Winnie, you've forgotten this. Winnie, what about that? Have you considered this?
Yeah.
And so we left this in the public for around 3 years and asked people, we begged people to find holes in this design.
To treat it kind of like a hive mind, like a
exactly. I mean, just actually, we asked be critical. Tell us what's wrong with this.
Yeah.
And so after 3 years, we then addressed all the remaining criticism, and then we published this. And we published this in a very high-profile journal, and it's very common to get a lot of media attention when that happens. But the night before we published this, the journal got in contact with me and said, you better be prepared for a lot of media attention, which kind of is strange. That never happened to me. That usually never happens. So I got this email and so I thought, oh, that's a bit strange. And I kind of wanted to go to a lecture of one of my colleagues that evening, so I stayed here a little bit longer. And around mid-afternoon, the phone started to ring, and it never stopped ringing beyond belief. And I think I sat here still till midnight on the phone with journalists. And
but
2
it's
days.
so exciting, and it's amazing to see. Yeah. What you've achieved as well, like genuinely, obviously studying under you and learning what you're doing, it blew my mind then. But the fact that now you're kind of leading this field, there's a big buzz, people are talking about this. This is something that you've been working for how long have you been working on this now? For
15, 20 years.
How do you feel getting to this point?
That's great. I mean, we are literally, it's a best time to be in this field. It's really, there was a time when nobody really believed that one can build a quantum computer. For many, many years,
because it was so unstable,
it's
because
so
it was
difficult, it's so challenging. The amount of stuff you require to build such a machine.
You went, hold my beer, and then you made one.
I love it. People tell me I can't do something, I love to do it anyway.
Yeah, exactly.
So this is great. Like, this is, as soon as somebody tells me this can't be done, then that is much more of a reason for me to do it anyway. So. And so I love challenges like that.
So I mean, you're obviously you're loving life right now, and everything seems to be flying at such a rate, here at Sussex. Where you're probably the best person in the world to answer this. Like, where do you feel this is going to be in 5 years' time, 10 years' time? Like, do you now have a much more concreted and solidified knowledge of what the real impact of this technology to regular people is going to be? Or are you still in a position where you just go, you know what, this is a kind of uncharted territory and it's quite hard to pinpoint what's going to go. How do you feel about that?
So once we released this first industrial blueprint, this was basically the first time anybody said we can now build quantum computers and here's how you could do it.
Yeah.
And since then, we've been working on building practical prototypes. And now, most recently, we actually started a company, a full-stack quantum computing company that will manufacture these devices. But I think it's best to think...
so that's already now in process where I imagine the patent and the legal stuff must be a nightmare, but like you're actually going to start constructing and building this for use for companies to hire to solve their encryption problems and stuff like that.
That's right. For use for many different purposes and fundamentally to make the world a better place, because there's many things you can do with quantum computers, or you hopefully will be able to do with quantum computers that is completely unimaginable right now. And many of the things you could would be tremendous possibilities. But think of quantum computers a bit like conventional computers, and it's best to look in history. So in the 1940s, people built first computers, and arguably Second World War was decided with conventional computers because the first computers decrypted the German Enigma code, which played a big role maybe in the outcome of Second World War. So people used first computers in the 1940s. Yet when I grew up in the 1970s or 80s, I didn't have a computer. I learned typewriting on a mechanical typewriter. So the first computers, the C64 and so on, they came around in the 80s.
Yeah.
So what I'm trying to say is quantum computers going to evolve very similarly. So it's not like there's not going to be one day when we have a quantum computer. We have quantum computers right now in my lab, but they're very small. They're literally just a few qubits. So they're going to slowly become more powerful, and they will allow us slowly to tackle more and more tasks. So it's not like from one day, in 5 days we'll have quantum computers, in 5 years we will have a quantum computers, in 4.5 years we won't. But
I'm with you.
we will have
it's a tricky question,
better and
right?
better machines, and they will become more capable of solving more and more problems. But equally, we have a lot of work in front of us in order to realize these machines.
But there's something that might be bugging me a little bit about, when you scroll back to the 1940s, I'm sure they weren't quite sure how this technology was going to be used. And then it obviously changed the world in such a drastic way. And it's relatively positive, because there's not particularly bad stuff happen from that development in technology. Now, when we start going into the territory of having systems, and the thing that resonates with me most when we talk about this in particular is what you said earlier about like a system that was particularly good at optimizing problems. Like whether we look at the traffic problem or the egg box problem, or you have now systems that have such outrageous ability to optimize in a way that classical computers can't do, humans can't do. Like the risk of sounding like at the risk of sounding a bit kind of like doomsday-ish, what happens if a system like that has the ability to kind of reprogram itself? What happens when it starts to optimize itself? And I'm kind of borderline into the sort of AI world here, but can you see how the mix, like AI is scary enough as it is, like with the capabilities that it can be used for now. You start to mix that with this infinite processing power that's able to figure out the optimization of basically any system, and you start throwing this stuff together. Is there any part of you that has any form of, maybe fear is a bit too strong a word, but do you think that maybe we are playing with something that might be, I don't know, a bit of a shock to the system when it actually starts to develop? Like, what if we have super intelligent AI that just takes over the world?
I think with any innovation, there has to be responsible innovation. So you shouldn't be just developing things without understanding the implications. And so there is actually an application of quantum computing in machine learning. So it's quantum computing.
But is it fair to say that maybe we never will understand the true implications of this technology, where it's going to go? Is that fair, or do you think that we've got a pretty? I
think we have to, and we certainly have to make an effort to understand the implications. Like any technology, art, AI, computing, like we see all the implications already, like, with the way how Facebook interacts with our lives, and how maybe even we are being manipulated in elections via bots and whatever not. So I think this is something we need to be on our toes about, and quantum computing is no different than other technologies in the sense that we need to be very careful about understanding its possibilities and regulating it sufficiently so that we stay in control. Now, AI obviously is an important topic, and there's all these visions about AI suddenly, taking over the world in some Terminator style kind of thing. And obviously, like, this is something to think about, to be careful about, but we can't also stop innovation, because if you look back at history of humankind, you can see that innovation has been capable of making our life much better in so many different ways. And the same way as computers can be used for terrible things, but it can equally be used for fantastic things. It's just important to understand the opportunities well enough that we can assure that we can limit use of this technology for things we don't like them to be used. So that's like with any technology. The quantum computer is no different than other technologies.
It's so exciting. So, it's probably not about, because I got to be careful. I could go down the rabbit hole and we'll be here for hours. But for everyone listening at home, connecting obviously with your story, how can people find out more about your work, and how can they get involved if there's a few maybe gaps in their knowledge or something that we might have skipped over? How can they learn more about you and what you're doing? So
it depends where you are right now. If you're in high school, go into your physics class and first of all tell your teacher that there's plenty more interesting things than what he's teaching you right now, and also know that, and get involved. Like we are right now at the starting point of really doing tremendously, unbelievably amazing things, making use of these very strange quantum effects, very similar to what you've seen in Star Trek. So if this is something interesting to you, then get on your math, get on your physics, and get over the boring stuff which you're going to have to do in high school in order to then go to university and do some really cool stuff like teleportation or entanglement or whatever not. And it's only going to get more interesting from here. So we need the very best minds to get involved. So that's certainly something, if you're interested to really get into this field, you should. There's plenty of stuff you can read about and learn about. I've actually written a part of a book on quantum computing. It's called What's Next. Awesome. So you can get that. But if you go on the internet and if you Google our group, IQT Sussex, or my name, Winfried Hensinger, you can get plenty of information. There's a episode of the Gadget Show, which is really nice. And there's plenty of stuff on the internet where you can read about what we do.
Well, I've got to say, thank you for doing this. It's been an absolute pleasure, and it's good to be back. I'm sure we're going to go and have a little look around the lab in a minute. But for everyone listening, that's a good time to wrap up. So thank you very much for coming in, Winnie. Catch you in a bit.
Nice talking to you, Mark.